Are there any questions? Oh, sorry. All right. Well, I want to review the Lorentz group and Poincare group and the Dirac representations and so forth. I'm following my treatment, which is very similar to Schwarz's treatment. I'm going to then double back and also present some of it the way Schwarz does. So the basic definition of a Lorentz transformation is that this is a 4x4 matrix A. Eta is the metric of flat space-time. L transpose eta L is eta. For an infinite, if L is 1 plus something very tiny, then this is what you have. So the somethings very tiny have to satisfy this relation, and for example, the generator of a rotation is this, the generator of a boost in the one direction, here a rotation about the one axis. You then write L equals 1 plus omega this way, and all those i's are because we have this physicist fetish of sticking in i's everywhere, making things Hermitian. And so we put in a minus I, and then we have to take it out with an I here, and we put in a minus I here and take it out with an I there. Then the j's turn out to be I times the r's. These are Hermitian, but then the k's, which are the boosts, are not Hermitian. And so the commutation relations that these satisfy then are, those are the ones for rotation. The boosts have one thing about them that's simple, namely ji kj is I epsilon ijk kk. So the boosts transform, there are three boosts, they transform as a three vector under rotations. And then ki kj is minus I epsilon ijk jk. This tells you that if you boost infinitesimally in one direction and then in another, and then go backwards in the first and backwards, then backwards in the second, the total thing is minus a small rotation about the other axis that you left out. The way a four-vector transforms is this way. On an infinitesimal transformation, you have an infinitesimal boost, lambda, and the space part are x plus t lambda plus theta crossed into x. So we have a rotation about the angle theta, which is infinitesimal, and a boost in the lambda direction, infinitesimal. This is the way time and space behave. Time is just lambda dot space. X is t times lambda, this is a vector, and then plus theta cross x, which you'd expect. Now, as we learned last time, if you define j plus or minus sub L as j sub L plus or minus I k sub L, then what you have is these remarkable commutation relations, namely the six generators of the Lorentz group decompose into two sets of rotation generators, or two sets of operators that obey the commutation relations of angular momentum, and moreover, and most miraculously, they commute with each other. So you have j plus I, j minus j equals 0. This means then that the representations of the Lorentz group are just sort of complexified versions of the rotation, of the representations of the rotation group, and you learn about them in quantum mechanics. They're these 2j plus 1 square matrix. The matrices that are square, and 2j plus 1 by 2j plus 1 for spin j, and j is 0, 1/2, 1, 3/2, etc. So this is a review, and how fields transform. Well, a general representation, of course, then, is you pick a spin for the plus rotation operator. I'm saying rotation, of course they're actually rotation plus boost. So for the j pluses you pick one spin, and for the j minuses another spin. You then have a representation here, and I'll use theta and lambda as the parameters for the rotation. So this is theta dot j minus I lambda dot k, which is what I should have written in the book. Instead I had explicit indices. And you can decompose this into e to the minus I theta minus lambda divided into j plus minus I theta plus lambda dotted into j minus. And so that's the general representation of the Lorentz group. These things are not unitary, but they're finite dimensional. Under a Lorentz transformation, we have a general field of two spins, j and j prime, and m prime of x, u inverse Lorentz transformation L is d j0 m double prime of L inverse d 0 j prime m prime and triple prime of L inverse times psi j prime and double prime and triple prime of Lx. So the space under a Lorentz transformation, a general field, the argument goes to Lx, but the spin indices transform as L inverses, and they transform in that way. Here, J, which is the actual generator of rotations, is J plus plus J minus, and K, the boost generator, is minus I J plus plus I J minus. Okay. Now, the two-dimensional representations, the left-handed one is 1/2 0, and notice the notation is you put the 1/2 on the left side if it's left. Here, what I have is theta lambda is e to the minus I theta dot sigma over 2 minus lambda dot sigma over 2. This is the boost part, this is the rotation part. And you can rewrite this simply as, just sort of generically, as e to the minus z dot sigma over 2, where z is a triplet of complex numbers. And here what we've got is J is sigma over 2, and K is minus I sigma over 2. So you see the generators of rotations are Hermitian, the boost generators are anti-Hermitian, because the sigmas of the Pauli matrices, which are Hermitian. For some reason, Schwartz has a plus here. I think I'm following Weinberg.
I think. But, you know, when you have plus or minuses in a lot of equations, there's always a possibility of a slip-up. Of course, it doesn't matter, because if we've got the wrong sign here, we just say something else by what we mean by lambda. But I think I'm using the right notation. As I said last time, the standard boost that takes us to P is R of P hat, a boost in the three-direction energy P0, and then an R inverse of P hat. And we can rewrite that as e to the alpha P hat dot B. And this turns out, this means that this D 1/2 0 of 0 and then alpha P hat is, which is this, it's just, well, it's actually e to the minus alpha P hat dot sigma over 2. And this turns out to be I cosh of alpha over 2 minus P hat dot sigma sinh of alpha over 2. I like to use the Russian abbreviations for cosh and sinh because we save writing O and S. Well, O and S here and I and N there. The Russians, of course, have extra letters in their alphabet, and they have one letter for ch and another one for sh, and that's why they write it that way. Anyway, this thing turns out to be P0 plus M minus P dot sigma over a square root of 2M P0 plus M. And under this D 1/2 0, the general D 1/2 0, D dagger 1/2 0 of theta and lambda minus I, this is just the identity, of course, D 1/2 0 theta lambda, this is minus I plus lambda dot sigma. So you see the identity operator, apart from a minus sign, is transforming like time under Lorentz transformation. And I should have written this in a 4-vector notation. Sigma these are infinitesimal theta and lambda. So this is sigma plus minus I times lambda plus theta at sigma. So the upshot here is that that SA, which is we can think of as minus I sigma, this transforms as a 4-vector under this matrix. This is for infinitesimal Lorentz transformation. And you might say, well, why does he care? Well, it's because then we have D adjoint 1/2 0 L SA being minus I and sigma, D 1/2 0 L is then equal to LAB SB. So in other words, this 4-vector under general 2x2 left-handed Lorentz transformation goes transformed like a 4-vector. And that's actually important. Now, if we look at this general way that a field can transform and we go to the simplest non-trivial case, what we have is U of lambda, U of L, C, this is a 2-vector field. U inverse of L is D 1/2 0 of L inverse, the 2x2 matrix,
on C of Lx. So if we put in explicit indices, this might be A, well, it would be an M, wouldn't it? M prime, M prime. Okay. So that's how a base, this is half of a, well, it's a massless Weyl spinor here. So it's a two-component complex field. Now, what's the action for this massless field? Well, the action density is I c dagger of x time derivative times I minus grad dot sigma on C. So, notice that this is essentially that 4 vector that we were talking about a moment ago. So in other words, it is, if I write it as a 4 vector, it would be actually minus, so it would be minus S A dA, where S is this. So grad gives us that, D0 gives us that, and the minus signs cancel. And this is important because this is why this action density is Lorentz invariant. When the field transforms this way. And in order to see that, notice that the field is going to L of x. So if we look at the action density of Lx, what are the derivatives in here? They're the derivatives with respect to x prime being Lx. So they're derivatives with respect to x prime equal to Lx. And L inverse, of course, on x prime takes us back to x. And so the Beef derivative that would occur in here, because it's a derivative with respect to x prime, is partial xb prime, which is partial xa, partial xb prime, partial xa. And now what is this? Partial xa, partial x prime b. Well, this thing is, of course, xa equals L inverse AB XB. So that the partial of XA with respect to, this is a prime, X prime B is L inverse AB. So this is L inverse AB, partial XA. Okay? And so now we can show that this thing is Lorentz invariant. Namely, U of L this would be I C dagger of L of x, and then it'll be a D1 half 0 adjoint of L inverse. And then we'll have minus DASA, which is what I wrote here. And now D1 half 0 of L inverse, this being 2 by 2 matrix, of course. And then C of Lx. And okay, and on the other hand, SA, D adjoint SA, D, remember SA transforms as a 4 vector, so this is I C dagger of Lx. minus dA, but instead of SA, what we have is L inverse AB SB C of Lx. And why L inverse? It's because this is D of L inverse, not D of L. And now we see that LA, L inverse AB is just, we just have here Lx, and this is minus D prime B SB C of Lx. And by prime, I mean the derivative with respect to the coordinates x prime equal to Lx. So that's why the whole thing is Lorentz invariant. Incidentally, that's also shows us why something like this, if this is a 4-vector and this is a derivative, this is a divergence, of course you know it's Lorentz invariant, but a way of seeing it here is that this is dA prime, B prime A, and dA prime is dB, L inverse BA, and BA prime is L A C BC, and so you see these guys are L inverse L, and so this is just dB delta PC BC, which is just DC VC. All right, so that's why this thing is Lorentz invariant. And this is part of the Dirac action. Let me show you why this C is left-handed. Its equation of motion is d0I minus del dot sigma on C of x equals 0. So this is, so to speak, the Dirac equation or the Weyl equation, or half the Dirac equation for a massless field. And now, if you just write this as e to the I p dot x, what you have here then is E plus p dot sigma C of p is 0. And if we multiply from the left by E minus p dot sigma, then what we get is E squared minus p squared, because p dot sigma squared is p squared. This is just p 3 vector squared. On C is 0, so E squared is p squared. That means the mass is 0. Okay, so this is a massless field. And okay, so since it's a massless field, E and P are the same, so we can rewrite this equation. And rewriting the equation, what we have is P over E dot sigma on C is equal to minus C. But now P over E is 1, and sigma is 2J. So this equation equivalently is P hat dot J on C is minus 1/2 C. So the eigenvalue of the angular momentum in the direction of motion is minus 1/2. Schwartz measured these backwards, but I don't know, maybe I'm backwards. Okay, so now we want a mass term for this field. And the mass term, it turns out that you have for this very simplest spin 1/2 field is called a Majorana mass term. And this mass term is, say, minus 1/2 m, and I'll write down two forms. C dagger, sigma 2, C star, plus C transpose, sigma 2, C. What?
It's all the symbols. That's
What?
all. It's all the symbols, that's all.
Yeah, you used everything.
Dagger and star and transpose and the thing itself.
Oh, you're right, yeah, I didn't realize that, yeah. All right, well, why is this Lorentz invariant? Notice, by the way, that this field has to be neutral, because this C would annihilate a particle, C transpose would annihilate a particle. If the thing has charge, then you've lost 2 units of charge, and that's not good. P&M would go bankrupt if charge. I'd be arrested, maybe shot, probably really out to the police, which may happen in any case. But, all right, sorry for all right, so let's understand why this thing is Lorentz invariant. Well, we saw that the Lorentz transformation was e to the, in fact, how did I write it? E to the, yeah, let's look back over here. E to the minus z dot sigma over 2. So this is, the minus sign is not important in this context. And then we have a sigma 2, and then this is that transpose. So it's C transpose e to the minus z dot sigma transpose. Notice my left arm is down, so you need to watch carefully. Now, if we transpose this thing, what happens? Sigma 1 is 0, 1, 1, 0. Nothing happens. Sigma 3 is 1 minus 1. Nothing happens. But sigma 2 is antisymmetric. So when we flip this, this is the same thing as sigma transpose e to the minus z1 sigma 1 minus z3 sigma 3 plus z2 sigma 2 because of the transpose rate. And then we have a sigma 2, and then e to the minus z dot sigma c. All right, but when sigma 2 goes through, if we pull the sigma 2 through, we flip the sign of sigma 3 and sigma 1 because they anti-commute. And so this thing is sigma transpose e to the z dot sigma, e to the minus z dot sigma c. So this is sigma transpose c, so it's invariant. So the Majorana mass term is actually the simplest mass term and it's Lorentz invariant. All right, for the right-handed boost, it's just the same thing that I just went through. You just change a couple of plus signs to minus signs. And maybe I could do that, instead of writing it all again, let me see if I can just do it on the fly. If I just, yeah, here's some colored chalk. I wish I had a different color, but anyway. What happens is, if you go to write, it's 0, 1 half, and you just get a plus sign here. The change over here is that you just change minus to plus if you go to 0, 1 half. This thing, the thing that's a 4 vector now, is simply plus 1 sigma is the 4 vector. So let me write down what the invariant action is, and I don't need to prove that it's invariant. So we have u of L, zeta of x, u inverse of L. This is d 0, 1 half of L inverse zeta of lambda x. And the right-handed action density is I zeta dagger of x, d0I plus sigma dot grad zeta of x. And under a Lorentz transformation, u of L, lambda r of L r of x, u inverse of L is just L sub r of Lx. So this is, I've got too many L's here, but the action density just changes by x going to Lx. And if we go through the razzmatazz about why this thing is right-handed, we have d0I plus L dot sigma. Zeta is 0. Again, In momentum space, it's E minus P dot sigma zeta is 0. So once again, it's massless, but now we have P hat dot J zeta of P is a half zeta of P. So this one is right-handed. And the Majorana mass term, though, for this thing is exactly the same. So there's no reason to fool around with that. Now, what Dirac did originally was to put both of these together. And so what he had was J is a half sigma 0, 0, sigma. These are the generators of rotations. The boost generators then are I over 2 minus sigma 0, 0, and sigma vector. And what Dirac did was he introduced these famous gamma matrices, the anti-commutator of gamma A gamma B, which of course is gamma A gamma B plus gamma B gamma A, is 2 eta AB times the 4x4 identity matrix, of course. These are 4x4 matrices. So any set of 4x4 matrices that satisfies this anti-commutation relation is a suitable, genuine set of Dirac matrices. Now what's really remarkable is that you can define Jij, well let me just define Jij as a combination of the JKs. So we're just turning a vector into a tensor here. And J0J is going to be Kj. So I just want to write the 6 generators of the Lorentz group in terms of a tensor notation. And then the remarkable thing, this is absolutely remarkable, is that JAB can be represented as minus I over 4, the commutator of gamma A with gamma B. And this thing is called the Clifford algebra. Who Clifford was.
He wasn't red, was he?
What?
He wasn't red, was he?
Wasn't what?
Red?
Did you ever read the children's books about Clifford the Big Red Dog?
No.
No? Well, you should go check.
I'm much older than you.
You have kids, though.
Well, no, you were a child once, correct?
Yes, when I
Yeah.
was a child, there weren't any books. It was before books.
He was before books. So you were like pre-Gutenberg? Is that what you're saying? That's
Yeah, actually, by the way, Gutenberg wasn't the first printer. It was actually the Koreans. Here's our Chinese friend here is.
But I don't agree.
But the Koreans, the Korean king, I forget his name. Do you remember his name?
No.
No. Sejong, I think his name is Sejong, but anyway, around, I don't know, 14th century, 13th century, he appointed a commission to invent an alphabet for the Korean language. And once the alphabet was invented, he promulgated it much to the displeasure of the upper class, which was sufficiently wealthy and educated to actually learn Chinese, and they could write Chinese characters. But the Korean people then could all read and write using this alphabet, and pretty soon they were printing, and they were actually printing before Gutenberg. Anyway, these are the generators, and
You didn't even read the Korean version of Clifford the Big Red Dog?
oh, Korean is not an easy language.
That's not
It's
true.
all
That-
vowels.
That's, I've been told that it's easy to read Korean. It's very difficult to speak it.
Well, it's certainly difficult to speak it.
Yeah.
It's easier to read Korean than Chinese, that's for sure.
There we go.
Because they have an alphabet. The Chinese, of course, should adopt an alphabet.
You can't say that on camera.
I have. Actually, when I was in China, every time I talked to the Chinese person, I said, you ought to adopt an alphabet. And every time, no was the answer.
Must be
Um,
English.
Okay, so in what sense is this true? It's that JAB with gamma C is minus I gamma A to BC plus I gamma B A to AC. So what this is saying is that the gammas, the four gammas transform as a four vector. That may not be totally apparent, but that's actually what that means. And another thing that this means is that these guys, written as commutators of gammas, satisfy the commutation relations of the Lorentz group, which is I, JAB, JCB equals A to BC, we'll derive this later, A to BC, JAD minus A to AC, JBD minus A to DA, JCB plus A to DB, JCA. You'll see this relation written several times in Schwartz's chapter 10, except that he uses G instead of eta and uses Greek letters instead of A, B, C, D. The gamma matrices, one representation, as I said, any set of four matrices that satisfy this anti-commutation relation is a suitable set of gamma matrices, and in fact, even more general. You can use either the flat space matrix that I use or the one that Schwartz uses, and either way you call them gamma matrices. Weinberg's choice is minus I 0, 1, 1, 0, where this is a 2 by 2 matrix, and gamma is minus I 0, sigma, minus sigma 0 for the other three. Now, of course, Weinberg has the minus 1 plus 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 matrix. Schwartz has the 1 minus 1 minus 1 minus 1 metric. So to go from Weinberg to Schwartz, all you do is cover up the minus i's, and then that flips the sign of eta. Okay. Now, this happens to be the form of the gamma matrices that's nice for seeing the Lorentz structure of the Dirac equation. And on the other hand, if you want to do the hydrogen atom, this is not the best representation. Also, there's another representation in which all the gamma matrices are real. That's called the Majorana representation, but with Schwartz's metric, they're all imaginary. There are stories about Majorana, but I don't really know them very well, so I'm going to try to repeat them. I think he disappeared somewhere in the 40s.
Yes.
Nobody knows whether he was assassinated or fell off a boat or died in a love quarrel. I don't know. Anyway, C zeta. Okay, so what Dirac constructed was really a 4-vector rather than these Weyl spinors. And you put a left-handed one up here and a right-handed one there, and you use these gamma matrices to do your Lorentz transformations and so forth. The Lorentz invariant action now is just the sum of the two action densities that I wrote down, and for left and right. And the way one writes this conventionally is to introduce something called psi bar. Psi bar is psi dagger gamma 0. What does this do? This just interchanges
put C with the zeta. So this thing is zeta dagger, C dagger. And so this is minus psi bar gamma A dA plus M psi. And Feynman introduced the notation d slash plus M psi. So slash, and I don't know really of a good way to do this in LaTeX, but slash on any 4-vector means gamma A with the 4-vector. Here it's dA. And so what is this in this particular case? It is I C dagger D0 I minus del dot sigma C plus I zeta dagger D0 I plus del dot sigma zeta. And why is it that things worked out that way? After we interchange the zeta with the C, you see the gammas are all off diagonal, so that stitches them back together again. So it's sort of a, it should be, might be possible to construct a better notation, but no one has as far as I know.
So what is the point of the slash?
The slash, just instead of writing gamma A dA, you just write D slash. That's all. And for example, A slash is gamma A. So it's a cute notation.
It has no purpose.
What?
I feel like it has no purpose whatsoever.
Yeah.
Except
Well,
to obfuscate
no.
understanding.
It
So if that's its
turns out
desired
you,
goal, then it has accomplished that, yes.
you have to contract many 4 vectors with gammas, and it gets really tiresome to write gamma upper A, 4 vector lower A. You just write a symbol
But
for
you
the
can't implement it in
vector.
LaTeX.
There is a LaTeX thing, it's just, I've had trouble using it, let's put it that way.
Okay.
It ultimately came down to LaTeX. That's why it's so good.
Absolutely.
I think there's a command for that.
There is.
I think so.
Excellent.
Well, why don't you tell me about it or us about it?
Maybe. I need to check the book.
There is at least one macro, but
Someone wrote the pieces on this.
It is a package.
all right. Let us notice something now. We've talked about left-handed spinors and right-handed spinors, and now here's something quite surprising. Suppose C is a left-handed spinor. Then zeta is a right-handed spinor. In other words, what you do is you take, and what does this mean? What is sigma 2? 0 minus I, 0. And what is C star? Well, it's C dagger, or adjoint, 1. That's what I mean by C star. Well, I'm using dagger for when, you plunge in the dagger, the thing falls over and lies on its side.
Right, but then what does it mean to take the dagger of a complex number?
It's just C star. So in other words, the star complex conjugates numbers, mission conjugates operators, but doesn't transpose anything.
Right.
See, like in this
No,
Majorana mass term,
I'm clearly just asking, why is there a dagger inside that column vector?
there's dagger, conjugation, transposition, and then nothing at all. It is an unusual notation, but I was happy to see that Schwartz uses it. I use it in my book.
Wait,
Oh.
so what are these things inside the column vector there?
This is the first and second component of C,
Are they numbers?
No, it's C1 is an operator,
Oh, okay,
and this is
okay.
the Usual
There we go.
conjugation conjugate of the operator.
Okay,
That's what it is.
much sense is being made now. Thank you.
Oh, you know, how many candies do you want a candy?
No, thank you.
I owe you at least one.
No, thank you.
Anybody else ask your question? I haven't been.
You gave clear insight into the discussion. That probably deserves some.
All right, let me get the candy then.
Yeah.
Yeah.
So another hour before dinner.
It is another hour before dinner. No, I'm okay with the operators inside matrices as operators, that's fine. I'm okay with that. I just want to clarify what these metrics look like.
It's gonna slash there and then yeah, cancel.
Did you
Use
have a
package
question?
cancel. No, I'm telling you how to do the slash.
Oh, really?
Yeah, use package cancel.
Use package cancel.
Yeah.
Cool.
See. Yeah.
All right, use package cancel. So it's a yeah, all right, so use package cancel.
Yes.
You should write it on the board. Now it will be recorded for all posterity.
Fantastic. Don't forget the
And the, all right, the example, let's do the example.
Yeah, I'm gonna say.
slash and cancel. Curly brackets, whatever you're gonna cancel with it.
Okay.
Yes, perfect.
Thank you.
Cool.
I owe you 2 candies.
Okay.
Just one?
As corn syrup, I don't need corn syrup, thank you.
Oh, yeah, you're absolutely right.
So can we make a request for the organic version of those things?
Organic doesn't help. I mean, organic.
No,
No, the ones at
fructose
Costco
is
that are
better.
organic don't have any corn syrup in them.
Well, they can make
Yeah, but
organic
organic-
corn syrup.
Yeah.
No, I mean, no, but the ones, the other version of those candies at Costco don't have any corn syrup in them. So
Oh, which ones don't have corn syrup?
the ones that say organic on them don't have corn
Really?
syrup, yeah.
Okay, I'll get it.
They're $2 more.
I'll get
but-
it. You guys are worth it. Okay, now, why, if this is a left-handed spinner, why is this a right-handed spinner? Well, in what sense is it a right? By the way, if e to the minus z dot sigma is a d1/2 0 left-handed, the corresponding right-handed is z to the z star dot sigma. This is the corresponding z1/2, 0 1/2, the right-handed. That's how they differ. And so the question is then, if c transforms leftwise, why does zeta transform rightwise? And the answer is, you have e to the z star dot sigma, that's the right-handed transformation, on sigma 2 c star. Well, what happens? When you move the sigma, this through the sigma 2, what happens? The sigma 1 and the sigma 3 change. So you have e to the z minus z1 star sigma 1 minus z3 star sigma 3 plus z2 star sigma 2 c star. Now we can rewrite that as sigma 2 big parentheses e to the minus z dot sigma c star. You see, because the star doesn't affect sigma 1 or sigma 3 and just changes z1 and z3, but the star on sigma 2 flips sigma 2 and flips sigma 2 star, and so we get plus. So this is why sigma 2 c star transforms as e to the z star dot sigma,
when C transforms leftwise as e to the minus z dot sigma. So that's how that thing works. Now, what's the simplest Majorana spinner? We can make a Majorana spinner this way. C sigma 2 C star. So this one is this is left and this is right, but there's only one field here. So this is taking a 2-component spinner and writing it as a 4-component spinner. Why anybody would want to do that is unclear, but actually it's not that unclear. It's that the gamma matrix algebra is so nice that you can treat left and right simultaneously. That's why people use it. But on the other hand, if you do it this way, then you've just got a Majorana spinner. And you can do the same thing with a zeta. You can do sigma 2 zeta star zeta, and this is again a Majorana spinner. And using this relation, what we see is that this is minus I gamma 2 psi Majorana star. So that's what a Majorana spinner satisfies, and this is saying the particles are the same as the antiparticles, no charge, and so forth. Okay, suppose you've got two.
Wait.
Yeah.
So do those things really exist?
What? I'm sorry, say it
Do
again.
those things really exist?
Well, we don't know.
We don't know.
Yeah, we don't know, I mean, the particles that we sort of know about, matter particles, are the quarks and the charged leptons. Those are Dirac, represented by Dirac fields, as far as we know. And we're pretty sure of that, but these are high approximations. On the other hand, the neutrinos are puzzling. And we don't know whether the neutrinos are their own antiparticles, then they'd be Majorana, or whether they're Dirac particles. And I think in some level, they've got to be Dirac particles just because the weakened Dirac symmetry takes an electron into a neutrino, and that takes a left-handed Weyl electron into something, and that's got to be a left-handed Weyl neutrino. So at some level, it's left-handed Weyl. But then after symmetry breaking, in the real world, you know, who knows what we've got. And it's just uncertain. Okay, so you remember that I stressed that if you had two massless spin zero particles, you had two spin zero particles, two scalar fields, each same mass, you could take a complex linear combination and make a charged scalar field. Okay, you can do the same thing if you have two Majorana spinners, and you can put them together into one Dirac spinner, and you do it this way: 1 over square root of 2 psi 1 Majorana plus I psi 2 Majorana, and so this is 1 over root 2 C1 plus I C2 and zeta 1 plus I zeta 2. And you can call this C Dirac, zeta Dirac. And now, this represents a charged field. This is a complex, this is an ordinary Dirac spinner. Now, what is the Dirac mass term? Well, let's see, did I do the, I didn't, all right, let me show you what the Dirac mass term is. The Dirac mass term is psi bar Dirac psi Dirac. And it looks nice and simple until you realize that this isn't psi dagger psi. This is psi dagger gamma 0, and so the thing is flipped. So this thing actually is M. I'm going to skip using the D, okay? Psi dagger C plus C dagger zeta.
where C is left-handed, zeta is right-handed. And now, why is this Lorentz invariant? Well, I think I'm going to have to go up to the front. We're on a board here. And let me erase some of the board. Now, what about questions? Maybe somebody has a question.
You gotta lean back. It doesn't squeak.
Yeah,
Was that a question?
I'm getting instructions on how to move the chair.
Yeah, well,
Yeah.
these chairs, I think, were a mistake. I think they were bought before one had the internet and Amazon. Of course, the other thing is that the university administration strangles the department with rules on purchasing. The only good thing about it, the only thing you can say in favor of these rules is that in the Air Force they're even worse.
That's true. That is true.
Okay, let's see why this this Dirac mass term is invariant. So we have something like this: zeta dagger C. Well, under a Lorentz transformation, and you could write this as, let's see, how was I writing it? Was I writing it as U first and then U inverse? This thing would go into, first of all, what does C transform? C goes as e to the minus z dot sigma. In fact, I put a 1/2 in there. That was silly. Forget that. Unfortunately, I caught it. Okay, so that's that. And zeta, well, zeta goes as e to the z star dot sigma zeta, and then the whole thing is daggered. Okay? And now, if we undagger it, this is z dagger, this will be z dot sigma, because the z just star becomes z, and the sigmas are all permission. So no change, except of course this is x, and this is evaluated at the space-time point Lx. So that's why the Dirac mass term is invariant. Because it was discovered before the mass term, the Majorana mass term that I described. Now let's take the Dirac mass term, but use it for a Majorana spinor. So then what we would have is minus 1/2 m psi Majorana bar psi Majorana. This would be minus 1/2 m, and what would it be? Well, it turns out it's zeta dagger c plus c dagger zeta. This is thinking of the Majorana field as C zeta. But on the other hand, the Majorana field, remember, has zeta, zeta is essentially sigma 2 C star and so forth. So this thing actually is minus 1/2 m C dagger sigma 2 C star plus C transpose sigma 2 C. One way of writing it, another way of writing it is minus 1/2 m zeta dagger sigma 2 zeta star plus zeta transpose sigma 2 zeta. And this then is the Majorana masses, which are, where was my Majorana?
Right. So this is the Majorana mass term. So in other words, if you take the Dirac mass term and use it for a Majorana spinor, it just gives you the Majorana mass. What does that mean? I think that means that the Majorana mass term is more fundamental. Okay, Poincare group. Well, that's just putting the translations together with the rotations and boosts. And so let us notice that the translations, if you translate in space and then go forward in time, or translate forward in time and then move in space, you get to the same place at the same time. Right? I mean, you can drive home now, wait 10 minutes, or you can wait 10 minutes and drive home. Either way, you're home in 10 minutes. Okay. So the translations of space-time commute with each other. And their generators then are H and the PJs commute. And of course, PI, PJ, they also commute, otherwise we never find our way around. So you can move the eraser here and then there, that's the same thing as there and then there, and either way you get the eraser to the same place. And the other thing is that H and P is a 4-vector, and so under a Lorentz transformation, E minus I theta dot j minus I lambda dot k, and let us make it infinitesimal so that L is equal to I plus theta dot R plus lambda dot B. So theta and lambda are small, and R and B are those matrices that unfortunately I just erased. Then what happens here to, in fact, let me do it this way. I plus I theta dot j plus I lambda dot k, all of that on the left, and the inverse of that, or the adjoint of, no, the inverse of that, minus I theta dot j minus I lambda dot k on the right. What is it? Well, this thing has to transform as a 4-vector. So what we have to have here is H plus lambda dot P and P plus H lambda plus theta cross P. And what well, of course I had that here and erased it, but it's that under an infinitesimal Lorentz transformation, a 4-vector HP turns into H plus lambda dot P, and P plus H lambda vector plus theta cross P. Okay, that's what we saw, and this is an example of it for the case in which the 4-vector is minus I sigma. All right, well, this allows us to figure out the commutation relations of the whole, of commutation relations of H and P with the rest of the Lorentz group. And so all you do is you just look at this, and on the left-hand side, you can write it in terms of commutators. And on the right-hand side, well, they're just operators. And so you can figure out what all the commutators are. In particular, you find out that JI with H is 0. So the time translation operator is invariant under rotations. You then find out that JI PJ
is I epsilon I j k dk. That means that the momentum operator is a 3-vector under rotations. And then, by considering the k's with these and what the and looking for the coefficients of lambda over here. In other words, you said everything equals 0 except for lambda. Then you get the commutator of k with h and p, and then you see what the lambda terms are here. You compare term by term, and let me show you what you get. Boy, that yellow chalk is unforgiving, isn't it? What you get is the commutator of ki with h is minus I pi. And the commutator of ki with pj is minus I delta ij h. Just can't erase it. And I'm using here 3-vector notation. In other words, this just means that if j is 3, this is just p in the z direction. These are, so in other words, these relations here, perfectly straightforward. These relations here are somewhat mysterious, not straightforward. And in fact, Weinberg had I don't remember quite where it was, but he was deriving one thing after another and then was saying effectively, you could really get somewhere if you could just figure out, everything would be so simple if you could just figure out what k was or what h was, or, and in particular he was looking at these relations and saying that arranging to have them was non-trivial. Okay, well, we also had, I derived earlier and erased the commutation relations for the generators of the Lorentz group. In fact, I think they're still there, actually. They're, right. These are the commutation relations. These are the commutation relations of the generators of the Lorentz group, written in terms of these of this two-dimensional notation, and we get this nice structure here. Of course, you can equally well write them in terms of j plus j minus, and then they're just two angular momenta. But so this is sort of the gilded lily version of them. But anyway, when you do that, so the gilded version of all these commutation relations then is I JAB JCD is A to BC JAD minus A to AC JBD minus A to DA JCB plus A to DB JCA. And then, much more simply, PA JBC is A to AB PC minus A to AC PB, and then PAPB is just 0. So this is the whole Poincaré group. These are the translations, these are the translations and the rotations. They go as a 4-vector, and then these are the rotations and boosts with each other, and they produce this totally mysterious and
intimidating commutation relation, but it's just, remember, it's just J plus and J minus two angular momenta effectively. So it's really much simpler than it looks.
Wait, so the Poincare group does not include the time translation operator?
No, everything's here. The time translation is P0.
Okay. Gotcha.
Okay, now, I think now it might be appropriate for me to skim over chapter 10 in Schwartz and include some of the things that he did that I didn't do. And so let me, actually, it's sort of almost the end of the hour. I was just thinking there's something cute to do. You remember this business of the covering group. You have SO3 as the rotation group, and SU2 is the same Lie algebra, but it's simply connected. And then there's the Lorentz group is SO3-1 or 1-3, and then SL2C, which is the thing we've been talking about, namely e to the z dot sigma. That's SL2C, determinant 1, 2x2 complex. Okay, there is a strange demo that I can do for you, I think. Does anybody have a belt that's really wide? How wide is yours?
I don't have a
Wider
belt.
than mine?
I don't have a belt. Sorry.
All right, let's
I
use
don't
my
know.
belt. Now, I need somebody to come up here and hold one end of the belt against it. All right, the TA will do it. All right. Now, I should have rehearsed this. Is this on camera?
I'm not sure. Not sure.
Turn it on. Turn it
If
on.
you aim the camera, he'll hold the belt. All right, this is Dirac's belt trick. And, okay, so if you rotate it once, wait a minute, let's do it, let's see, is this rotating it once? Okay. Now, it's got something in it, and, yeah, you have to hold that down. And is there,
Probably exists.
oh, shit, I've forgotten what the trick was. It's something like, if it's rotated, let's see, 180 degrees, 360, and it's, all right, let's just, the idea was that this one is easier to, well there, I untangled it very easily. On the other hand, that's right, I untangled it without undoing it. All right, let me just show you again. So if you do it 360 degrees, this, I mean, obviously you can untangle it by just reversing the rotation, but you can't straighten it out otherwise. I suppose you could come around this way. No, you see it's still twisted. Okay, but on the other hand, let me just show you one more time then. If you do it once, twice, and then again and again, you can just pull it back and then forward, and bingo, it's okay. So, what this means? No idea. And in fact, Schwartz, in some place in chapter 10, Schwartz has something where he says, hold a glass of water and go around 360. I could not, do you understand what he said?
Yeah, it's just that.
All right, you do it with this glass of
Oh
water.
my, I know, I'm not gonna use a glass of water because then I'll freaking drop it.
All right, I'll drink the water.
Right, so you start here, and then you do once, and then you do twice, and you're back.
Yeah.
That's not, you just have to have the requisite joint flexibility.
All right, I thought he meant something like this, and I was trying to do this, and I couldn't figure out what was going on. All right, so anyway, if one of you guys wants to do a demo of the Schwartz example next time, that would be welcome, I guess. Now, what this is showing, by the way, is, let me just mention, that if you have e to the, let's see, simply e to the minus I theta dot sigma over 2, this is the rotation matrix for a spin 1/2 system. If you have an angle of 2 pi, then this is e to the minus I pi dot sigma. Let us just say pi sigma 3, say. So then this is e to the minus I pi, e to the I pi, 0, 0, and this is minus 1, 0, 0, minus 1. So a rotation of 360 degrees for spin 1/2 is just minus 1, but e to the minus I, instead of 2 pi, 4 pi, sigma 3 over 2 is e to the minus I 2 pi sigma 3, and that's just 1, or if you want, 1, 0, 0, 1. So that's what is somehow illustrated by the belt trick, but what it means, I don't know. And also, it suggests that there's something right about string theory, but what that is also I don't understand. So I think we can just quit with that. All right, so any questions?